Okay, today we're going to do a walkthrough of the Cast AI Kubernetes optimization platform. So by default, we have a tour that you can go through, but today we're going to do a guided tour. We're going to onboard an actual Kubernetes cluster and take it end to end through the entire optimization process. So to start with, we're going to connect our cluster. Click the Connect Cluster button. We support EKS, AKS, GKE, and COPS on AWS currently. Today we're going to onboard an EKS cluster. Everything we do here today is also available to be done on Terraform. Many of our customers use Argo CD and Terraform to do their onboarding, but today we're just going to run through the scripts to go through the demo. So this first phase of the onboarding, we're going to be running this deployment. So it's going to create a Cast AI agent namespace, and it's going to onboard the resources that we need to be able to use this platform. The cluster role is entirely read-only for this first phase. It's just get, list, and watch verbs. So this first piece can make no changes to the Kubernetes cluster whatsoever. I'll go ahead and run that in my Lens terminal. Okay, so we just went ahead and created the deployment. This cluster had already been onboarded to phase 1 in the past. That's why these were unchanged. But then we also added the agent back into the platform. So you can see we ran the script here, and now we're connecting in the background. You can see the cluster is connecting. Now what this agent is going to be doing is it's going to collect a mapping of the pods that are running on the cluster. It's going to look at requests and limits that are on those pods, labels that are on those pods, and look at the node sizing that's on those pods and send that back to our SaaS platform so that we can analyze and look for optimization opportunities. Okay, we'll go ahead and explore this cluster. Okay, we're still connecting here. It'll take a few more seconds. Currently, this cluster costs about $1,900 a month using AWS. If we optimize this cluster just using on-demand, we would be able to save 29.8% down to about $1,340. If we were able to use some spot instances on the spot-friendly workloads, we would be at $431.94. And how we determine spot friendly, we look at the actual Kubernetes workloads, and we're determining whether they have a stateful Kubernetes attribute to them. For instance, are they writing to local disk? If they're writing to local disk and we move that pod, there could be a loss of data there. So this is based purely on what we see in Kubernetes. We do not have access to see inside of the pod to look at the actual application that's running. So there are possibilities that your application could have stateful attributes to it within the code, but not within Kubernetes. So these are obviously just suggestions. We recommend that our customers look through the suggestions and determine which ones are actually going to be favorable on spot versus which ones might not be. In this case, about 8 out of 10 of our workloads appear to be good to run on spot. Now the optimization that we're talking about here, it would be going from 6 C5 2 extra larges and 6 M5 larges. You can see the cost per CPU here, CPU hour rather. And now we're going to be moving, the ideal situation on this cluster would be 1 C6A large and 2 C5A 4 extra large spot instances. And you can see the drastic difference on CPU cost per hour on spot. It's significantly less expensive than the on-demand instances. Okay, now right now we're just looking at the free tier. So everything that we can see here is part of our free tier platform. So you can see the dashboard here. This is all available to be exported using metrics. Now, if we go ahead, we can look at the cost monitoring dashboard. See, we have some data from yesterday, a little bit of data from today. This will track costs over time on the cluster. As the cluster moves up and down, obviously today we don't have very much data in here yet, but we'll be collecting more data. Now we can also break down costs by workloads, so you can see exactly what your different pieces of your application cost. In this case, the checkout service is using the most CPU and has the highest cost per CPU. And right now it's at just under 33 cents so far for the month. But again, this will continuously collect data going forward. This cluster has not been onboarded very long. And then lastly, we can also break down by namespace. You can see what the applications within a namespace are. This is great for tracking costs by team. If you have multiple teams using different namespaces, you can see what their aggregate cost per namespace is. Or if you just want to see which workloads are costing you the most money, you can check the workloads here and identify where the biggest offenders are. That way, as you're trying to tune your operational costs, you know exactly which pieces of code and which teams to talk to that are going to be the best value for tuning those costs. It's much more effective than kicking off a 50% or 20% across the board when some of your teams might already be running very lean. Now, lastly on this piece is we have our security report. So on here, you'll be able to determine different security issues with your Kubernetes cluster. This is part of our read-only portion today. In 2023, we'll be moving this to a automated remediation of security best practices. So you can see here we've identified some different CIS benchmarks that we're violating, most small issues, and there's some vulnerabilities in the applications that we're running. And again, this is part of our free read-only tier. Okay, next, we're actually going to onboard into the automated piece of the platform. So again, we're going to run the script in this case. This is going to deploy a Helm chart, as well as set up a cross-account role bind for AWS. We can open the script that we're going to run right here. So in this case, we're going to create the policies that we need, set up the roles that we need, and we're going to set up the AWS permissions where we can actually add and remove instances from the cluster to be able to do the optimization. So this can all be done in Terraform. Today, we're just going to do it in the script. Copy this and run it in my Lens terminal. This typically takes about 1 to 2 minutes to run. Okay, we have successfully sent the credentials back to the platform. We've auto updated on this side. We can start optimizing. We offer a full and scoped autoscaler. Most customers opt into the full autoscaler. Scoped is best if you have a very large dev cluster and you want to do a proof of concept on a small piece of it. But in general, the full autoscaler works the best and provides the best savings and the best optimization. We're going to go ahead and start the setup. Our policies are very simple to understand. We have a lot of configuration that can be done through pod configuration, but the actual policies to manage the cluster are pretty simple. We're going to go ahead and turn on the unscheduled pods policy. We can set cluster headroom. In this case, we don't really need this. This gives you a little bit of extra space in the cluster for scaling into. It's going to allow you to be able to have a little bit of extra CPU and memory to scale. In this case, we're just going to leave it at 0. We do want to use spot instances on this cluster. So we're going to enable spot and preemptive. We're also going to enable spot fallback. The spot fallback functionality, if there's no spot inventory available, will automatically migrate the workloads to on-demand. This way you never have an out-of-capacity issue. However, it's also going to allow you to move automatically back to spot instances once there is spot capacity available on the market. In this case, by default, we're at 30 minutes. So every 30 minutes, we will check to see if the spot capacity has become available and migrate back to spot once it is. Okay, node constraints are going to allow you to target certain size nodes. So by default, you want to keep your options as open as possible, particularly when using spot, so that we can select the best cost instances. However, there might be cases where you don't want two 32 core machines holding all of your load. Maybe you don't want anything above, say, a 16 CPU and 128 gigs of memory. Maybe that's the biggest you want to go. So in this case, we can set our node constraints here. We're going to go ahead and save that. We'll come back to the node deletion policy in just a minute. We do have the ability to narrow down the selection of nodes. So for instance, if you need to use have just a spot setup and you want to use only compute optimized nodes. Well, compute optimized nodes are going to give you just the C families of nodes and allow you to target those. You can also do storage optimized, or you could include or exclude any families that you want. This is really going to allow you to target specific workloads around specific use cases. Um, Typically, segregation is not going to help your costs, but if you do have specific workloads that have to run on certain types of platforms, you can select that through here and set up the templates that you need. Okay. We're going to go ahead and kick off a rebalance on this cluster. Rebalance is what's going to get us to an optimal state quickly. So in this case, it's going to do a blue-green deployment, and we'll show the before and after in just a second. We're going to do all 12 nodes. You can do either all or partial. So if you only wanted to do 9 nodes, you can do that. In this case, since it's our first time on this cluster, we're going to go ahead and do a full rebalance. I'm going to generate the plan. Okay. So in this case, we do have some workloads that are spot compatible. So we're going to generate 2 C6A large on-demand instances, 4 INF1 2 extra large instances, and 1 M5 extra large spot instance. In this case, you can see how inexpensive this INF1 2 extra large is. They're 1.35 cents per CPU hour. And then this M5 is 1.7 cents per CPU hour, but it's a better size. It's the number of CPUs that we need. So we're going to go ahead and kick this off. It's going to create our 7 new nodes first. So it's going to go ahead and build those 7 nodes. Once they're ready and have joined the cluster, you can see over here they're starting to create. Once they're online, they will be able to start taking traffic. So once these have fully joined the cluster, we will do a graceful drain on these remaining nodes and migrate the workloads across. So you can see right now we're at 49, 50, 60% CPU utilization on most of these nodes, and kind of similar on the memory side of things. The goal is to get to as close to 100% CPU and memory utilization as possible. Your workloads are protected by the requests that they put out there on the pods. And so the goal is to pack those requests in as tight as you can. So as this runs, we'll let it run in the background as it's creating nodes. One of the big things that Cast AI is going to be helping with is the downscaling. So we'll go ahead and turn on the node deletion policy, and let's discuss what the evictor and node deletion policy do. So we're going to go ahead and save this and turn it on. Now, the way Cast AI downscales is it's going to evaluate every node in the cluster to determine whether or not those nodes can be removed from the cluster safely. So we're going to show a quick example of a real-life customer example. So on the left side here is using cluster autoscaler. This is actually a GCP cluster, a Google cluster. So you can see during the day they were peaking at about 2,800 CPUs. They were only requesting about 1,700. So about 1,100 wasted CPUs that were unutilized during the daytime. And when they scaled down, they went down to about 349 CPUs at night, but they were still provisioning almost 1,800 CPUs. So you have 1,400 CPUs here that were completely unutilized during the nighttime. They onboarded to Cast AI right here. This is the new scaling curve. Much better compression, much better bin packing during the off hours, and then more effective scaling during the daytime. We're tighter to their needs. We still were able to meet all their pod affinity and anti-affinity rules, which is why there's a bit of over provisioning here. And then during the nighttime, it's much tighter downscaling again. Okay. Go check out how our rebalance is doing. So we've successfully created all the nodes. So now we're going to be moving forward with draining nodes. Okay. So you can see these nodes are all cordoned and drained. They're migrating the workloads over to our new nodes. And this is going to follow all of the rules of Kubernetes. It's using the Kubernetes scheduler behind the scenes to do these drains and moves. So if you have pod disruption budgets or topology spread constraints, those will all be obeyed during this process. This rebalance process is not mandatory by any means, but it's going to get you to a better state much more quickly. Just letting the autoscaler and the downscaler do their thing over a couple of weeks will get you fairly close. But this is going to get you the best defragmentation in your cluster that's possible. Think of it like, in the late 90s when you ran a defragment on your hard drive. This is going to get you that best defragmentation, that best compaction, and then the autoscaler will take on going forward to actually manage the cluster. So you can see some of the nodes have already finished draining. You can see there are empty nodes in here. Okay, and our nodes that we provisioned are getting filled up. So once this has completed, we'll go ahead and delete off those old nodes. And then once they're all deleted, then that'll be the new cluster going forward. And that's how the autoscaler will then take over from there. Okay. You can see we onboarded a little bit yesterday, and today we're onboarding again. This graph over time will show you how much over provisioning you have. So the goal is to converge these two numbers from provisioned and requested to be very close to each other. Okay, we've deleted off our extra nodes. You can see the rebalance has completed. The cluster has moved down to $478 a month from $1,900 a month. So that's $1,400 a month savings. You can look at how tightly packed our nodes are here. So we're running at 77, 76, 92% across the board here. So pretty tight compaction. There's not a lot of extra room for other pods to run in here. And you can see we're at 90.3% optimal. That's likely due to the fact that some of these nodes, the C5As, likely were not available, or they have moved in price, because the savings report is going to work off of some cached data, whereas the rebalance will run off of live data that's available. And lastly, all the actions that we saw here are available in the audit log. So you can see exactly what everything's doing. You can look at the JSON of what's happening here. You can get very detailed logs of everything that's happening in the autoscaler. And we can look at our node configuration. If you need to customize subnets or security groups or instance profile ARNs, if you want to add additional tags to your instances, for instance, tagging it for specific cost reporting purposes internally, or using a different AMI, that can all be configured in the node configurations. You can also have multiple node configurations. You can set up kubelet parameters here. So overall, this gives you all the functionality you need to be able to fine-tune those instances that you're creating. Okay, that's everything we have to show today. You can see in our cost monitoring that we've drastically decreased our costs. The normalized cost per CPU will decrease over time. And as we let this run and collect data, we'll be able to get a better idea of what the long-term cost of the cluster is. Thank you.